Continuing with section 7.4, let's look at an example which appeared earlier, and that is the one with the chocolate chip cookies. And so here we have a sample of 40 chocolate chip cookies, and the mean of the chocolate chips is 23.95, and the standard deviation is 2.55 chocolate chips. So we are supposed to construct a 99% confidence interval to estimate the mean number of chocolate chips in all of such cookies. Okay, so from the sample data we know that the mean is 23.95 chips. The standard deviation is 2.55 chips. The sample size is 40, so it gives us a degree of freedom of 39. The confidence level is 99%. That means alpha is 1% or 0.01. And alpha divided by 2 is then 0.005. Our critical value t sub 005 would then be 2.70. So what we do here is we look at the 39 degrees of freedom, and we go to 0.005, and there's 2.708. So that's our critical value. So then our margin of error is equal to t sub alpha divided by 2 times the standard deviation, sample standard deviation divided by the square root of n. So it is 2.708 times 2.55 divided by the square root of 40, and that is equal to 1.09 chips. Now, our confidence interval is the sample mean minus the margin error to the sample mean plus the margin of error. And when we substitute the values for the mean of 23.95 and the margin of error of 1.09, then our 99% confidence interval is 22.86 chocolate chips to 25.04 chocolate chips. The next exercise is about the movie Harry Potter and the Half-Blood Prince. And the movie opened on a Wednesday, and the amounts are listed in order for the first 14 days of the movie's release. Use the sample values to construct a 99% confidence interval estimate of the population mean. What is the population? Identify at least one major problem with this data set. Okay, so we can proceed in one or two ways, and in fact I will be doing both. If we want to do this manually, of course we need to compute the sample mean first. We need to find the mean of all these numbers here. And when we do that, it turns out the sample mean x bar is equal to 16.357, and that is in millions of dollars. And we find the standard deviation from however we want to compute the standard deviation, that is equal to $14.52 million. Okay. Now we have 14 samples, so n equals 14. That means our degree of freedom is equal to 13, and the confidence level is 99%. So that means alpha is equal to 0.01 or 1%, and our alpha divided by 2 is equal to 0.005. And so when we look up our critical value t sub 0.005 for 13 degrees of freedom for this level of alpha, then we find in the table we find 13 and 0.005, so it would be 3.012. 3.012 is our critical value, 3.012. And so our margin of error is equal to T sub alpha divided by 2 times S divided by the square root of n. So it would be 3.012 times 14.52 divided by the square root of 14. And so that margin of error is $11.69 million. So our confidence interval for the population mean is the sample mean minus the margin of error, less than the population mean, less than the sample mean plus the margin of error. So when we substitute our values for E and for the sample mean, then we come up with a confidence interval of 4.667, less than the mean, less than 28.0405. So that is our confidence interval, and that's in millions of dollars. So the question is, what's the major problem with that? Well, it really appears to have a distribution that's really far from normal, so that might not be a very good estimate of the population mean. And so the sample values are not really simple random samples either. That's from the first 14 days of release. So the confidence interval is probably not a very good estimate of the population mean. Another way to solve this problem is with technology, and I did that also. And so for that, I input all the values that are given here in my Inspire, TI Inspire, which is basically the same as a TI-84. And so that came out to 4.7, less than 28.1, and that's millions of dollars also. So technology is a little bit, it's essentially the same if we round this up to 4.7, which is certainly appropriate, and this could be rounded up to 28.1. So this is manually, and this is with technology. So in other words, the differences are negligible. And I'm doing it this way so to give you a chance to do it yourself using the given data and see if you can come up with the same answers. For the next one, the numbers of years in college listed are the numbers of years it took for a random sample of college students to earn a bachelor's degree. So it's based on data from National Center for Educational Statistics. So construct a 90% confidence interval of the mean time required for all college students to earn bachelor's degrees. Does the confidence interval contain the value of 4 years? Is there anything about the data that would suggest that the confidence interval might not be a good result? So here I just use technology. In other words, I input the data in my TI Inspire, and it came up with a confidence interval between 5.14 years for the mean and 7.86 years. So that's using technology. Of course, you can compute the sample mean if in case you're interested in doing that. The sample mean for this one was 6.5, and the sample standard deviation was 3.5 years. So these are all in years. So then, of course, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 13, 14, 15, 16. So n was equal to 20. So our degrees of freedom would be 19. So you can, and we have a 90% confidence level. So alpha is equal to 10%, and alpha divided by 2 is 0.05. So then we simply need to look up our critical value for t. T's 0.05 for 19 degrees of freedom. So you can look that up yourself just as a practice run and see if you can come up with the same confidence interval. The next example deals with cell phone radiation, and that's always, the media often presents reports about the dangers of cell phone radiation as a cause of cancer. So here we have 11 cell phones and their radiation levels, and we are supposed to construct a 90% confidence interval estimate of the population mean. What does the result suggest about the Federal Communications Commission standard that cell phone radiation must be 1.6 W per kilogram or less? That would be watts per kilogram. Okay, so from the data that we have here, when we compute the mean, that is equal to, the mean is equal to 0.938 watts per kilogram, and our standard deviation is equal to 0.423, and n is equal to 11, so our degrees of freedom is 10. And since we have a 90% confidence level, we know that our T sub alpha divided by 2 is equal to T sub 0.05. And when we look at the table, for a degree of freedom of 10 for 0.05, it is 1.80. Let me move it up for you. 1.812. 1.812 for degrees of freedom of 10 and for 0.05. So 1.812. So our margin of error is then equal to margin of error is 1.81 times 0.423 divided by the square root of 11. So our margin of error is equal to 0.2308. And then we find out that our confidence interval is equal to the sample mean minus the margin of error, less than the population mean, less than the sample mean plus a margin of error. And when we substitute the values for E and for our sample mean, we find that our confidence interval is from 0.707, less than the mean, less than 1.169 watts per kilogram. So that is our 90% confidence interval. And what it really says is that that is certainly below the standard that the Federal Communications Commission has set as 1.6 watts per kilogram, so we're certainly way below in 90% of the cases. Of course, it also means there could be individual cell phones that exceed the standard of 1.6 watts per kilogram. So as a last example, we look at the mean IQ of professional pilots, and we want to determine what sample size we need to make certain estimates here. Okay, so we are told that the Wechsler IQ test is designed so that the mean is 100 and the standard deviation is 15 for the population of normal adults. Find the sample size necessary to estimate the mean IQ score of professional pilots. We want to be 90% confident that our sample mean is within 3 IQ points of the true mean. The mean for this population is clearly greater than 100, and the standard deviation for this population is probably much less than 15, because it's a group with less variation than a group randomly chosen from the general population. So if we use sigma as 15, we are probably very conservative by using a value that makes the sample size at least as large as necessary. So we assume then that the standard deviation, the population standard deviation is 15, and determine the required sample size. Does the sample size appear to be reasonable? Well, we know the sample size can be approximated by z sub alpha divided by 2 times the standard deviation divided by e, the margin of error, all squared. Okay. So our critical value, z sub alpha divided by 2, since alpha is we have a 90% confidence level. So we are looking for z sub 0.05. 0.05. And again, remember, we're looking for the z sub alpha divided by 2, in this case z sub 0.05, because we cannot look at t sub alpha divided by 2 because we don't have the degrees of freedom, because we don't have the sample size. So remember that for this estimate we use z sub alpha divided by 2. So we look that up in the tables, and that's 1.645. So we just substitute the given numbers that we have for E being 3, the margin of error. That's about 3 IQ points. So that's our margin of error. And we are told that our standard deviation is 15. So then N would equal 1.645 times 15, our standard deviation, divided by 3, and now the whole quantity squared, and that turns out to be 67.65 rounded. But remember, we always need it rounded up to a nearest integer, so the sample size should be 68. And so the last question is, does the sample size appear to be reasonable? Yeah, a sample size of 68 is reasonable. This concludes samples for section 7.4, and this also concludes chapter 7.